So at the end of the last class, I was telling you that we were going to learn a new statistic. We're actually going to learn two new statistics. And the reason we need to learn a new statistic is that the two that we've been previously using, the z and the t, they only refer to means. They can hold negative values, they can hold positive values. But variances, they can't be negative. Right? At the smallest they can be is 0, that they don't exist. They can't be negative. So because of that, we need to have statistics that also can only be positive. And the first one we're going to learn about is called the chi-square statistic. The chi-square is actually the square of a standard normal. So think of a normal distribution that has been squared everywhere. Okay, chi-square, square of the standard normal. In other words, it's like z squared. Right? Because z is the standard normal, so it's like z squared. The way we calculate chi-square, if we had to find our observed chi-square, is we would take n minus 1 times the sample variance divided by what we think to be as the null. And we see that this thing here is distributed chi-square with n minus 1 degrees of freedom. The n minus 1 should be familiar to you because that's the degrees of freedom associated with the sample variance. So that same degrees of freedom is used for the chi-square. This Greek letter here is chi, that's what it's called that. It too can be used into a confidence interval. In other words, if we want to know what the confidence interval is for sigma squared, we can use a critical value of chi above and below a certain threshold. So here's one example. Let's suppose that you have a sample of earnings for married couples, and you want to test if wages for married women and single women have the same volatility, meaning do they have the same variance associated with them. You find a study that states that the wage variance for married women is $10,000. You ask 21 single women their wage and find a sample variance equal to $14,400. To test if these two variance terms are the same at the 10% level, we need to find chi-square of 20. So 20 degrees of freedom with 5% in the tail, and 20 degrees of freedom with 95% in the tail. Use the chi-square table, and if you do that, you're going to find that chi-square with 20 degrees of freedom at the 95% is going to be at 31.41, and at 5% is going to be at 10.851. Our null here was that sigma squared would be equal to 10,000, right? That was the claim. And we want to see whether or not the sample variance is going to be equal to that. Our sample variance was what we got when we asked the 21 women, single women, what their wages were, and we took the variance, and we got 14,400. So then what we want to do is we want to calculate the statistic. The statistic is going to be n minus 1, so 21 minus 1 giving us 20, times our sample variance, so the 14,400, and dividing through by the null, which was 10,000. We get a chi-square of 28.8. Does that fall in between our critical values?
Yes.
Yes. So, we would fail to reject the null hypothesis that they have different variances. We would fail to reject the null hypothesis that they have different variances. The other reason you can use chi-square is for a measure called goodness of fit. Right, so let's say that you do go out and you get a survey, and you want to see whether or not that survey is representative of the population. And there's another survey that's already been done that you just don't have access to, but you know is a better measure. So let's say, for example, you wanted to go out and do a survey at Louisville. You go ahead and you do a random sample, you collect your data on the folks, and when you do that, you want to compare it to the census, figuring that the census did actually go and ask everyone, right? That's just a little too expensive for you to do, but you can go ahead and trust the statistics in the census and see whether or not they match up. So we can construct a measure to see how well our survey matches up with that of the census. Here there's one example. There is a survey called the General Social Survey. It's only done once a year, and it asks different people every year, but it asks them all types of different questions, like what party affiliation do you have, how many times you've been married, how often do you go out on dates, do you hit your kids, all types of stuff. You laugh, but they ask that question. Like, do you consider it an appropriate level of punishment? Do you consider a death penalty an appropriate level of punishment? All types of questions like that. Right? Well, before we make conclusions about whether or not people like to beat their kids or have the death penalty, we want to see whether or not it actually represents the population. So, we're going to take the General Social Survey, and in it we find that, in the population we find that there are about 80% of the population is white, 12% is black, and 8% is some other race. That number is changing. So this is our expectation. In other words, if we were to go off and we were to ask 2,386 people what their races were, we would expect, if they followed up with the population, that about 1,908 of them would be white, another 286 of them would be black, and another 190 would be something other than those two. Okay, that's what we would expect. Now we have the data from the General Social Survey, so we have actuals as well. We can go and we can count how many people declared themselves as white, how many people declared themselves as black, how many people declared themselves as other, and we can put those in. And then what we're going to do is we're going to essentially create this statistic here. We take the observed measure, we subtract off the expected measure, and we square it, and we divide by the expected measure. When we sum those together, that statistic is also a chi-square. And we can test to see whether or not there is a difference between the two. Make this a little smaller. So here we find a chi-square of 7.51 with 2 degrees of freedom. The 2 degrees come because we have 3 groups. And we have to subtract off 1. And our p-value, or in other words, the chi-square associated with 7.51. Let's go ahead and do that. .51 with 2 degrees of freedom. And we want true. It is 0.97. It's a huge number. Alright. We want to see if that's true relative to a p-value of 5% or an alpha of 5%, and we can say no, these data are not consistent with the proportions. And if they were, we'd be able to fail the rejection model. They should be very close to one another. Clearly, we're way off. So what this would say is that the General Social Survey would be a bad measure if we wanted to represent this particular population. Okay. Having said that, we're doing a study on 2 samples, not 1 sample, right? That's what we've been doing so far. Chapter 10 and 11 have been 2 samples, not 1 sample. So we have to still introduce yet another statistic. In this new statistic, we're going to be taking 2 different sample variances and kind of asking the same question. Are married women equal to single women when it comes to wages, or at least the variance in their wages, instead of picking a particular null? To do that, we have to construct a new statistic, which is an F statistic. An F statistic takes the sample variance from the 1 sample divided by n, divided through the whole thing by the sample variance of the 2nd sample divided by its sample size. So here, for example, an F test is used to determine if there is a statistical difference between 2 sample variances. This test is very important in linear regression, which is our next chapter. In linear regression, we are trying to choose the correct set of explanatory variables that minimize the variance between predicted and observed values of the dependent variable. So one of the things that we use an F statistic for is to say, how good are we doing? How much better are we actually predicting an outcome? To give you a sense of how you could use this, back in 2006, Netflix put out basically a contest. Right? They said, here is a subset of our data. Here it is. If you can find a better metric to predicting the quality of movies given past experiences or past ratings, we'll give you $1 million. And they went ahead and they had a competition. But you had to be better than their current level. So they knew what their current level was. They had that internally, right? So they had, if you will, their own S squared 1. Right? They had that. And what they did was they went ahead and they put this contest up, and it took several years. So although it was posted in 2006, it wasn't won until 2009, and it was won by 7 statisticians from different countries. So they're all working on it from different places, and they all came together, I guess, I don't know, somewhere. One was from Israel, another one was from Russia, another one was 2 or 3 were from the U.S., and another one was from Europe somewhere. They all came together, and they came up with an algorithm, and they were able to show with their algorithm another S2 squared. Now the question was, are you better? Right? Are you better? So here we're trying to reject the null hypothesis of having equal variances. We want one to be better than the other. In other words, you want this F stat, if you were to put a smaller number in the denominator and a larger number in the numerator, to be very big. If it is very big, then you can clearly say that the one in the denominator is smaller, statistically smaller, than the one in the numerator. So they did this. Now, how would you do it if you had to think about it? You guys now have enough statistical knowledge to make up a decent algorithm. All right? So let's think about how these Netflix things are set up. Go ahead and pause this for a second. Pause integrity. So population variances. We want to test whether or not 2 variances are equal to one another. This is going to be S squared 1 and S squared 2. In order to do this, we need to take the ratio of the sample variances. The closer that ratio is to 1, the closer they are equal to one another. The farther away from 1 it is, the more likely they are not equal to one another. Now the F-stat has a set of degrees of freedom for both the numerator and the denominator. Again, I would tell you to always stick the bigger number in the numerator. That way you only have to check one tail. You're basically asking yourself, is this significantly bigger than an F of 1? And that's going to depend on the relative sizes. So you're going to have a rejection region and a do not reject region, just like we did before. If you have an equal to sign, then you're going to have an F stat where alpha divided by 2 is going to be over here on the right side. Technically, you should have another one on the left-hand side, but if you follow my rule, you can ignore that. You'd only be checking the right-hand side. Right? If you don't follow the rule, then you would have to check both. Because in some cases, you'll have a value that's less than 1. Right? One-tailed test, same thing. Since you determined which one's on the top, you can do a one-tailed test, always going to the right-hand side. Just make sure you put the bigger number in the numerator. And so, here's an example of a New York Stock Exchange. You're a financial analyst for a brokerage firm. You want to compare dividend yields between stocks listed on the New York Stock Exchange and NASDAQ. You collect the following data. Is there a difference in the variance between the New York Stock Exchange and NASDAQ? Now, why would you care about the variance?
Fluctuation.
All right. Okay, so if you're picking a portfolio, one of the things you worry about the portfolio is the average return. And the other thing you worry about is how volatile is that return. Okay? If it has an average return that is low and high volatility, that's a crappy portfolio. Because you never know what's going to happen to it. If you have an average return that's very high with a very low volatility, you can make a whole lot of money. Usually those two things don't coincide though. Usually you have high average returns with high volatility and low average returns with low volatility. But here we want to find out basically which one has less volatility. So if we have a standard deviation of 1.3, we can square that to get the sample variance, right? We can also square the NASDAQ number to get its sample variance. We also know the degrees of freedom given by the sample sizes. So, first we want to find the critical value. Do that first before you calculate your F statistic. You're going to have a degrees of freedom in the numerator of 21 and the denominator of 24.
Don't we want the 24 in the numerator?
Not the degrees of freedom, the actual value.
Okay.
Alright, so if we go back, I would prefer to have this one in the numerator.
Okay.
Alright. So you go out to the table, you find F alpha over 2, or 0.025, with 20 degrees of freedom in the numerator, so that's going across the top, and 24 degrees of freedom in the denominator, so that's the first column going down, and you get an F of 2.33. You then take the 1.3, square it, take the 1.116, square that, and then you get your F value, which is 1.256. That lands inside in the do not reject region. So we would fail to reject the null hypothesis that there's a difference in the variances for the New York Stock Exchange and for the NASDAQ. Now in a model, in our next section, in a model, the reason we use this a lot is that you're going to come up with a linear regression. What that means is that you're going to come up with a dependent variable and a bunch of explanatory variables. You're going to use that to say how well can you predict the dependent variable. Alright? Now in some cases you're going to want to compare one model to another. You're going to want to say how much better can my model 1 predict the dependent variable versus model 2. Now they may include different amounts of information, right? They might include different variables. You can still compare the two by checking out their variances. You can still compare the two by just comparing their variances. The one that provides you with the smallest variance is the better model. So that's where the F test is going to matter a whole lot more.